So what we're going to talk about today is the law of conservation of mechanical energy. I am not going to teach you anything you don't already know. There is nothing new to add to this from what you did in Science 10. Okay, so if you found those roller coaster questions very easy in Science 10, you're going to love this because it is exactly the same. Why? Because the law of conservation of energy hasn't changed. It still says energy can't be created and energy can't be destroyed. So yeah, there's not really much more we can do with it, understanding that initial mechanical and final mechanical are going to be equal unless you do work, which we already covered. Okay, so we got to understand that obviously energy can't be created or destroyed. Energy can be converted from one form to another. Most commonly, that is some form of potential into kinetic or vice versa. Okay? And then we'll do some problem solving, okay? Using that to calculate mechanical energy and other variables that have to do with the energy of an object. Okay, so we calculate mechanical energy by adding together kinetic and potential energy. That's not new. We were doing that last week when we did our work energy theorem problems. Okay, last week we were doing this. Okay. We were doing problems that involved calculating work using the change in mechanical energy. If no work is being done, then that means we're dealing with what we would refer to as an isolated system. That means energy is not being gained or lost by any means in the situation we're talking about. If there's no energy being gained or lost, that means your initial mechanical energy and your final mechanical energy have to be equal. Okay, because you're not doing any work on the system and adding energy, and nothing is having work done to it by the system, which would represent a loss of energy. Okay, this is an isolated system where all the energy stays in there. So all that can happen is kinetic and potential keep getting turned back into each other. Okay, so if this was a roller coaster, this is a roller coaster that once you let it go would never stop. It would just continually circle the track because no energy would ever be gained or lost. Okay? Now, that would probably be nauseating because you could never get off the ride because it would never stop. That would mean it would have no brakes. Okay? Because it would just keep going and going and going and going. All right? Everybody okay with that? So, if we're dealing with that kind of a roller coaster, when we are up here, okay, we have a lot of potential energy because we have a lot of height. Yeah, okay, we're high off the ground. Being high off the ground means we're going to have lots of potential energy. More than likely here, our kinetic energy will be fairly low because we won't be moving very fast. Okay? As we go down that hill, and there's no friction, no other non-conservative forces, okay, that potential energy will get turned into kinetic. If I get down to ground level, how much potential energy will I have? None, right? And my kinetic energy would be at its maximum. Okay? Then I cruise along here and I go up this little hill. Well, if I go up this little hill, I'm going to gain a little bit of potential energy because I'm going to lose a little bit of kinetic. All right. Let's say I had 1,500 joules worth of mechanical energy in this position. How much mechanical energy do I have here? Taylor? You were right. 1,500. Okay, and here? Still 1,500. Okay? All that changes is how much of it is kinetic and how much of it is potential. The total can't change in an isolated system. Okay? Now, here's the issue people usually have with work energy theorem problems and conservation of energy problems. they have a hard time telling them apart. Okay? And the reason they have a hard time telling them apart is you get kind of the same information. You're going to get initial height and initial speed and final height and final speed. Okay? You're going to get a lot of the same variables. So it's the wording and context of the question that allow you to determine if it's a conservation of energy question or if it's a work energy theorem question. So you might want to add this to your notes somewhere. Okay? A conservation of energy question will never use the following words: force, work. Okay. The reason a conservation of energy question will never use those two words is because forces do work. And in a conservation of energy question, there's no work being done. So they'll never give you a force, and they'll never ask about work or give you work, okay? If you see those words, it's a work energy theorem problem. Okay, because then there's something that is changing the energy. Some force is either doing work on the system and adding, or is having work done to it, okay, and the system is losing energy. Okay, but if you see any mention of force or work, okay, then you're talking now a work energy theorem problem. Could I have a question that was a part A and a part B and have one of them be a conservation of energy question and one of them be a work energy theorem question? I could very easily do that because they ask for the same variables, but one of those things would say work or force. Okay, whereas the other one wouldn't. Okay, so like if the part A needs you to calculate something like final speed, then part B would go, you know, this happens, or the object slows down or comes to a stop, how much work is done? Well, you did a conservation of energy question, now it's asking you, okay, using what you calculated using conservation of energy, do a work energy theorem problem. Okay, but the way you can tell them apart is look for the words force or work. A work energy theorem problem will almost always contain those two words. A conservation of energy question will never contain those two words. Okay? All right. All right, so final mechanical energy and initial mechanical energy are always going to be equal in a law of conservation of energy question. Okay, so you might see things like there is no friction, or the track is frictionless, or something like that that would imply, hey, there's no way for this system to lose or gain any energy. Okay, so that is going to be constant along that path between the 2 points. Right, so if this thing is going through this track, maximum potential, minimum kinetic here, okay, down at this point, maximum kinetic, minimum potential, and then as you go up this loop, okay, you're going to lose some kinetic and gain some potential. So how will your speed here at point B compared to here at point A? Where will your speed be greater, A or B? A, yeah. It'll be greater at A because you have more kinetic energy at A. Once you go back up this hill, you're going to slow down. All right? You're not losing any energy, you're just turning it back into potential. Okay? And in fact, in the design of roller coasters, you have to be careful when designing it to make sure that you don't make any other hills on the roller coaster or any loops on the roller coaster higher than the first hill, or even anywhere close to the height of the first hill. Otherwise, you won't get through them. Okay? If you lose energy going down that first hill, okay, and you do in the real world, okay, and you don't have enough energy to get through that first loop, you could get, you know, either by, it's unlikely you get stuck at the very top, but you like might go up and then come back down, okay, and not get through the whole track. Right? Does that sort of make sense? Okay. Okay, now, you already all know that I'm a complete nerd. Okay, and I'm okay with that, and it's okay that you know that. Okay, I also used to coach track and field. And we went to provincials in Edmonton, and in the shot put area was this device. And I looked at it and like, oh, that's pretty cool. And then I watched them for a little while, and every time they put a shot put right here and let it go, this isn't the cool part, okay? It would roll down the hill, that's not the cool part, okay? And then it would roll along this level piece of track here, and just as it got to the end of the track, which was right at the throwing area, it would stop. There was nothing there to stop it, it just rolled to a stop. Okay? And it didn't matter what size of shot put they put on. The girls shot put, the guys shot put, the juniors, the seniors, it didn't matter what size of shot put, it worked the same for all of them. What was slowing the shot put down on the level piece of track? Friction. Okay? This was an example of somebody had calculated how much energy the shot put would have when it was at the top of the ramp. And then they used that to figure out how long they needed to make the track. Okay? So that it would lose all of that energy to friction along that track and come to a stop at the very end. Nobody ever got their toes, hurt by a shot put rolling off and landing on their toe. Okay? It's not like the bowling alley where you can get your fingers crushed in between the balls when they come flying up the return track. Okay? It would just slowly roll to a stop. So I watched this a little bit, and then nerd me kicked in. And I went and got the whole team. You guys gotta come see this! It's so cool! And then they're like, what? And then I explained it, and I'm getting the same reaction from you that I got from them. Are you kidding me? You made me come all the way over here. I was warming up, Coder. Like, it was, yeah. But it worked, because I actually found out later, they had this designed and fabricated at the university. The engineering faculty designed it, and then it was fabricated in the metal fabrication area, okay, so that it worked perfectly. Okay? It was just a conservation of energy situation. Okay? They knew the object would have no kinetic energy at the top of the ramp. They knew how much potential it would have. They knew the coefficient of friction, steel to steel. Okay? So they knew how much energy would be lost to friction along the length. Okay? And so all they had to do was bring the shot put over there, put it on the top, and let it roll. Okay? Every single time it worked perfect. I never did see it in the rain, though. How might it have been different in the rain?
Because the water between them.
Yeah, it might have changed the coefficient of friction. When the steel was wet, it might have actually rolled off the end, but I never watched them do it during the rain. Okay, but I mean, obviously they only build it for one weather condition. Okay. All right, so in this situation, it's a good example of potential energy being turned into kinetic energy. Okay, so we would know the kinetic energy here at the bottom. Okay, and then there's a perfect example of a question I could give you on a test. Right? Here's the height of the ramp. How long does the thing need to be if the force of friction is this many newtons? Okay, there's a part A and a part B there. There's a conservation of energy question to figure out how fast it would be going here, and then a work energy theorem question for the length of the track. Okay, that would be solving for distance when you know the force and the energy. Okay, making some sense? Okay, you thought I was a nerd, now you know it. Okay, and I'm okay with that. That's who I am. Okay, so applications of the law of conservation of energy. Okay, when the Olympics were hosted in Vancouver in 2010, there was actually a tragic accident that occurred on the first day when they were training the skeleton. Okay, the skeleton guys were doing their trial runs. They had got freezing rain overnight, and it had coated the track in this ice that was even lower friction than the ice they would have seeded it with a hose to make the track. So it had gotten this extra coating of really fine deposited ice on it from the freezing rain. And the first skeleton person that went down on the training run was killed because they were going so fast at one of the corners, faster than the track was designed for, that they flew out the corner and were killed when they crashed. Okay, so how do they fix that? It's not like you can just go and throw sand on the track. I mean, these are high-tech sleds and stuff. You're not just going to throw rocks and crap like that on the track to lower the friction. What do you suppose was the simplest solution so that they wouldn't be going so fast at that corner? how fast you're going at that corner is dependent on how much energy you have at that corner, agreed? How can you make sure you have less energy at that corner? Start lower. Right? If that person had too much energy there, that was a combination of the initial height of the track and obviously how fast they could push the sled before they jump on it. Well, if you make everybody start a little bit lower, nobody has enough energy to leave the corner. Everybody just started a little lower. Okay? And then nobody flew out of the track. Make sense? Simple application, right, of conservation of energy. It's like we used to, I don't know if they still do the soapbox derby here in town, like down the Veterans Way. We used to call it Shell Hill, but now it's Veterans Way. Okay, so you don't want to have people going too fast at the bottom, right? Well, there's little kids on their carts. Okay, so you have to make sure that the hill's not too long. Okay, otherwise they'll be going too fast at the bottom. They'll stop. Okay, they also obviously stop traffic. You don't want that Elizabeth Street to be going. That would be bad too. Okay, but yeah, it's just a matter of, you know, if we're going to have something like that, we have to know how fast an object could get going based on where did they start. Okay, so we kind of, that's how we apply that to a lot of different situations. Okay, here's what we got to get out of this. So this is bobsled, okay, start up here, and if they just jump in, obviously in the regular bobsled, they push the bobsled, so they would have an initial velocity of something, okay? They would have 600,000 joules of mechanical energy there at the top, okay? Down here, they still have 600,000, but what changes? Well, they're speeding up, so they're getting more kinetic, but they're lower, so they have less potential, okay? These two numbers are always going to add up to 600,000 joules, okay, in a conservation of energy situation. Okay. Questions on that? Okay, before we do this one, get up and walk around a little bit. Okay, so having watched Robbie Knievel jump, let's say that this is the situation. He is going 38 meters per second when he jumps off of that side. Now here it's showing him moving horizontally, and that one he was at an angle. Does it matter? How fast you're going determines your kinetic energy. That doesn't matter which way you're going. That's how much kinetic energy you have. Okay, so they drive off at 38 meters per second. They're 70 meters above the bottom of the canyon. When they land on the other side, they're only 35 meters above the bottom of the canyon. See if you remember from last year's roller coaster questions, because this is basically a roller coaster question. Calculate how fast they're going when they hit the ground on the second side. Okay, I will give you this tip. Their initial mechanical energy and their final mechanical energy are equal. Okay, and remember that we talked about this last week. That means that this is true. Whoop, that should be an I. Okay, so using what we learned last week and what you learned in Science 10, see if you can calculate for me what their final speed when they hit the ground on the other side will be. I'll give you a few minutes. All right, so here's what we know. Okay, we know the initial and final energies are equal because there's no mention of work, there's no mention of friction or anything like that. Okay, I'm looking for VF, which would be part of that term there. So what I need to do is, first off, isolate my kinetic energy final by subtracting potential energy final to the other side. So I'll have EP initial plus EK initial minus EP final equals EK final. Okay? Now I can put in the formulas. So I'll have M times G times H initial plus 1/2 MV initial squared, okay, minus mg H final equals 1/2 mv final squared. Okay, now, you guys were asking me, well, what's the mass? Which is a legitimate question. Mass is in every term, which is why I didn't give it to you. If it's in every term, I'm multiplying everything by that number, yeah? Does that mean I can take it out? if you're not comfortable with that on a quiz or a test, I would absolutely give you the mass. And you could plug it in till your heart's content, all 4 times. Okay, for me, I don't like having to put in extra work. Okay, if I'm punching that number in 4 times, that's 4 more times I got a chance to make a mistake punching something into my calculator. So I am going to get rid of it. Take mass right out of there. Now I want to isolate VF. So all I have to do is divide both sides by 1/2 and then square root. Okay, so what I'll have is that VF will be the square root of 9.81 times 70 meters plus 1/2 times 38 squared minus 9.81 times 35 meters divided by 1/2. Okay, so if I do that, I should get their speed when they hit the ground on the other side. Okay, when they hit the ground on the other side, the 3 significant digits, 46.2 meters per second. Okay, ringing a bell from last year? No? Okay, well, that's all right. You'll pick it up real quick. Okay, this is just like a roller coaster question that you would have done last year. All we're saying here, guys, to start this is the mechanical energy and the mechanical energy are equal. It's not changing because no work is being done, and then it's just algebra from there. Okay, we're just manipulating in order to find the one thing we don't have. Okay, now just to prove to you that if I had put in the mass, that it wouldn't have made any difference. Okay, what mass did I say? 175? Okay, so if I did that whole calculation again, but I put the mass in there, okay, I get exactly the same number. So 175 times 9.81 times 70 plus 0.5 times 175 times 38 squared minus 175 times 9.81 times 35, close the brackets, divided by 0.5 times 175. Okay, I got slightly, did I mess something up? Did I make a typo somewhere? Okay, must have made a typo somewhere. Anyway, okay, I made typos, but I don't know where. Okay, should come out to the same number every time. Okay, everybody with me there? It's a terrible demonstration. It was close. I'm sure I just missed something somewhere. Where did I screw up? No, it won't show it to me. 32. That's where I messed up. It's supposed to be 35. So that's why I came up there. We can fix it. Okay. And then Coderre will be right and vindicated. Okay. All right. Making sense? Okay, hopefully it's going to ring a bell. It's just a matter of practice, guys. Like, the stuff we were doing last week mathematically is actually more difficult than this. Okay. Okay, let's have you guys try number 2. It's very much like the one we just did. And then we'll walk through number 3 together, just because there's something in number 3 that's kind of important for us to realize, okay, and kind of understand about energy. But try number 2 for now. It's very much like the one we just did. Okay, so if I'm kind of like reading through this and writing down my givens, I'll write down the mass to be 55 kilograms. Probably not going to need it. Okay, is 225 meters above the ground, moving at 36 meters per second down. Now, they gave me velocity, and they said down. Does it matter? No, because if it was going up, by the time it came back down to that same height, would it also be going that velocity down? What goes up must come down and do so at the same speed. So here's the thing you need to remember about energy. Energy is vector or scalar? It's scalar. Okay, direction doesn't matter. You have energy, you can do whatever you want with it. Okay, direction is not a part of it. Okay, so we've got speed 36.0 meters per second, initial height, sorry, that's initial speed, 225 meters. Use conservation of energy to calculate its velocity, so I'm looking for VF, when it's 115 meters above the ground. Okay, so this is exactly like the motorcycle jumping the canyon question we just did. Okay, so I'm going to say EI equals EF because this is how the question told me to solve it. Incidentally, I won't ever do that. Okay, if I want you to solve it a certain way, I'm probably going to make you figure that out. Okay, so we're going to have initial potential plus initial kinetic equals final potential plus final kinetic. Okay, and given the context of that question, I don't think any of those are zero. Okay, I have initial height and initial speed, so I have both kinds of energy initial. Okay, and I'm not on the ground at the end, so 115 meters, I still have potential. Definitely going to be moving at that point, so none of these are zero. So I need to isolate EKF, so I'm going to bring EPF over to the other side. Okay, so I've isolated the final kinetic. Now I can put in the formulas, m times g times h initial plus 1/2 mv initial squared, okay, minus mg h final equals 1/2 mv final squared. Mass is in every term, so even though I was given the 55, I'm going to cancel it, divide both sides by 1/2, and then square root. Okay, so VF will equal the square root of 9.81 times 225 plus 1/2 times 36 squared minus 9.81 times 115 divided by 1/2. Okay. Okay, so I'm looking at, they'll be going 50, we have 3 significant digits, 58.8 meters per second. Okay? All right, now, number 3. Number 3 gives you a ton of information, and it actually makes it seem like it's much, much harder than it actually is. I would say part A is probably the hard part. Part B is basically the same thing we just did. All right, I'm going to give you a few minutes to give this one a try. Do B first. Okay, do part B first. You don't need the answer from part A to do part B. And then we'll talk about part A together. All right, so I'll give you a few minutes to do part B there. Okay, using the information you have. They do give you the mass. Okay, so you have it there. Right, but I'll give you a few minutes and then we'll talk about it. Equals EP final plus EK final. Okay, so all of that stuff that's still kind of applying here, even though that's our final speed now. Okay, so I'm going to subtract the EK final over and leave EP final there. Okay, so EP initial plus EK initial minus EK final equals EP final. That's all I'm asked to get. I'm not asked to calculate his height, just his gravitational potential energy. So, here is a situation where I can't cancel mass. Is mass part of your energy? Right? Which has more energy? A bus moving at 30 kilometers per hour or a child on a tricycle moving at 30 kilometers per hour? Which is amazingly fast for a kid on a trike. The bus, because the bus has more mass. Okay, so mass is still part of this thing. Okay, so all I have here is this. mgh initial plus 1/2 mv initial squared minus 1/2 mv final squared equals the thing I'm looking for. Okay, I just plug in my numbers and I'll have it. So 56 kilograms times 9.81 times 15 plus 1/2 times 56 times 21 squared minus 1/2 times 56 times 19.7 squared, okay, and that will give me, okay, the energy, which is right here, okay, that'll give me the 9.69 times 10 to the 3 joules. All right, so it's a question, and here's the point of doing it. A, it reviews a little bit of projectile stuff, so that's always good, okay, but the second thing, it illustrates that energy is scalar. Okay? It doesn't matter that he's not moving upwards. He still has kinetic energy because he's moving. Period. Okay? Direction doesn't matter when we're dealing with energy. The V in 1/2 mv squared is speed. Okay? Your direction does not matter for your energy. It matters for the work needed to take it away, but it doesn't matter for the energy involved. Work is also scalar, but the force used to take it away would be vector, is what I meant. I didn't mean to imply work was vector. Okay? Everybody with me there? All right, so tomorrow you're going to be working on a few questions with Mr. Deirdre. Okay? And then on Wednesday we'll do the final, or the unit exam review, and we'll talk about power. Power is super easy. You really only need to know what it is. No calculation. Okay. So if we can establish, which we have, that at this point, their highest point, they still do have some kinetic energy. Okay, that they're moving horizontally. Right. I can calculate what that kinetic energy is. Okay, and I'm still going to do a calculation like this. Their initial potential plus their initial kinetic equals their final potential plus their final kinetic, but I'm going to make the final point now here instead. Okay, and I'm going to find his potential energy, not his height, at that point. So we're going to go initial potential plus initial kinetic, okay, equals final potential, which is what the question wants, plus final kinetic. So I just need to solve for this. I'm just going to bring this over to this side. I'm going to bring EK final over here. All right, so I'm going to have EP initial plus EK initial, okay, minus EK final equals EP final. All right. Now, if I'm plugging in my formulas here, I'm going to have M times G times H initial plus 1/2 MV initial squared minus 1/2 MV final squared equals EP final. Here, I cannot cancel mass because it wants me to find their energy. And energy is dependent on mass. Okay, I mean, think about it. What has more energy? A bus moving towards you at 30 kilometers an hour or a person on a bike moving towards you at 30 kilometers an hour? The bus, it has more mass. Okay, so mass matters. I have to include it this time. Okay, now I have these numbers. I have these numbers. What I don't have is that number. That's the one we established would be their horizontal component of the launch velocity, because at that point, they're only moving horizontally. Okay, so all I have to do to calculate that is go the cos of 20 times 21, right? That'll get me the horizontal component of their launch. So we'll do that. Okay, cos of 20 times 21. Okay, so there's their horizontal velocity, or the velocity final in the case of this question. Okay, so now I can plug in my numbers. The person had a mass of 56 kilograms times 9.81 times their height, okay, initial, which was 15 meters, plus 1/2 times 56 times 21 squared, their initial speed, minus 1/2 times 56 times 19.7 squared. Okay, 56 times 9.81 times 15 plus 0.5 times 56 times 21 squared minus 0.5 times 56 times that speed there squared equals. Okay, so I have there 9.6, well, they have 9.69. For me, that looks like 9.68 times 10 to the 3 joules. They probably rounded off their speed, which they shouldn't have done, which is why I got a bigger number, or sorry, why I got a smaller number than them. Okay? Everybody with me on that? Okay? Would I ever give you one like that on a test? Absolutely not. But it's a good way to illustrate this. Don't pack up yet. It's a good way to illustrate this. Energy is scalar. The direction you're going does not influence the amount of kinetic energy you have. Just how fast. Okay? Up, down, sideways, doesn't matter. You're moving at that speed, you have that much kinetic energy. Okay? That's all we needed to get out of that. Okay.